permission slips?
Yes.
I'm collecting permission slips. Yay,
Wait, is it that for
Yes.
yeah.
Guys, I have an announcement. The next code of honor, does anyone know what the theme will be?
Yes.
No, unfortunately not. It's going to be disaster theme. So think of any horrible scenario you can possibly think of, even my nuts one. And I want you guys to try making skits for it. So don't leave me hanging and just try to make, just a random skit you can think of about disasters. All right? Thank
Anything else have something they need to announce before we get started? Then if you would be so kind to sit.
All right.
You have one.
Is there a way to turn off part of the lights?
Yeah, we can do that.
Everybody.
Ooh, the
Wow,
lights.
you turned off
Not yet,
all the
Papa.
lights.
Still need the ones up there. There's a few guys where I lost my goal.
There's the other.
Yeah, I couldn't see it, but
They're getting the bird out.
What's why did it happen? They didn't have wood then. You have to take the wood out. Yeah, right, they get the wood. Is it a rock band then?
Okay. Coolest merit badge, right? This is easy. For me at least. You guys are going to love this. Okay, I'm Tom Rooney. You guys probably all know that. I think everybody does. So I'm going to talk about what it takes to get, part of what it takes to get the Robotics Merit Badge. And the reason I'm doing this is because I've taken the Wood Badge course, and it's one of my goals to get my ticket, is to talk about this, and then another part of it is to take the troop on an outing to competition. So we'll get into that in a moment. So I've got worksheets that you guys can kind of follow along, and maybe make sense of what I'm talking about or take notes. Got some extras, I think. So, let's see. A couple of the really exciting things right now is that robotics is moving really quickly. It's probably one of the fastest developing areas of technology. Actually, as far back as '04, the Dartmouth Grand Challenge was run, and that was a race across the I can't think of the desert, the Mojave Desert from LA to Vegas. And the first year, lots of teams, Carnegie Mellon, Stanford, Oshkosh Truck, all attempted this and they all failed. Nobody was able to have an autonomous vehicle drive across the desert. And they were supposed to run this challenge every 2 years. Nobody wanted to wait that for a second year. They wanted to do it the next year. And the next year it turned into a race. Stanford won that. The guy by the name of Sebastian Thrun moved from the Carnegie Mellon team to the Stanford team, and then he actually went on to Google to work on that autonomous vehicle. So that was a really successful approach to getting this technology to advance. We have a challenge like that. RoboCup's another one that's been going on a long time. The challenge is come up with a team of robots that can beat the World Cup team in soccer on an official playing field in a real game. That's been going on since '97. They're not there yet, but they are using humanoid robots now, so that's pretty exciting. And it will get there. Another thing driving this is there's a maker culture. I don't know if you're heard of this, but people are making things out of electronics and mechanics because they're able to. There are 3D printers. There's electronics capability. There's all kinds of information on the internet that you can get and put together your own robot. So if any of you, how many have actually built or worked with a robot?
Yeah.
2, okay, 3 kind of, right. So you haven't done it, but you can. Everybody here absolutely can and will if they want to earn this badge. You have to make a robot. You have to design it yourself. You can't be a kid. But you all can do it, and there's enough information out there to find where I can help all of you. So actually, maybe the most exciting part of this is that we are now Team 3800A. I'm trying to find our placard here. Oh, I lost it already. Anyway, we are Team 3800A, and we've been granted use of all of this VEX robotics equipment to compete. And we'll be competing on February 2nd in Batavia in the Midwest Championships. Very little time to get ready, so everybody that's interested, we got to get moving on this quickly. So to give you an idea of what's going on with the Grand Challenge, there's now a robotic challenge that DARPA is running, and that's to create a humanoid robot that can perform disaster recovery. And this is this is the platform they would use. So this is way better than the Asimo Stride, although that's really an impressive robot. I've got some video of that. But this is going to be used by a variety of teams to actually drive a bobcat, open a door, climb a ladder, walk on a catwalk, shut off a working valve with water spraying everywhere. And this is the challenge that they're using. So there's also going to be a virtual challenge that's open right now. In June of this year, they'll have open pretty much the general public to participate by just downloading the environment and then developing the software. So that's this at the latest stage of this. So this has got external power, but it's got arms you can kind of see pushing on the walls. Is that the Terminator or what? You can run away from them, though, currently. Yeah, you can walk, amble away, no problem. So far. So that's using an arm against the wall. You can see that other arm out there. Boston Dynamics will supply that for the challenge. Well, the rope is for the safety if it falls, so it doesn't damage the robot. It was not actually holding the robot up. It didn't have the tension. You couldn't have held that up easily with that pulley. And it had another arm out there, but it also was supplying power. They're not fully independent of power. They have other equipment that is. But so you've got handouts. I'm covering 4 areas for the Merit Badge, 4 requirements: safety, robotic applications, or industry. General concepts and curves. And I'm going to try to fly through this because I don't have a lot of time and a whole bunch of stuff to cover in this. So safety. How might a robot be dangerous? Well, that would be dangerous. Yeah.
On the chemical malfunction, like with the wires.
Might get shot. Yeah, or you get sparks.
Hoping maybe short edge.
Yeah.
Or the possibility that robots become intelligent.
Right. They become self-aware. But even before they're alive, you might be working with them with various hand tools. And so it's just, this is obvious stuff, but you need to be aware that if you're using power tools of any kind, you want them to belt with you. They can be dangerous. Soldering irons, part of some of the electronics. Sean and I soldered the motor controller that's on this one robot here safely. So you have to be aware of that. There are also electrical issues, obviously. You can get short circuits that'll destroy your robot for one, but you could also, if something was powerful enough, many robots are powered off of the wall or higher voltage. You can be electrocuted. You should never work on any robot that's got power. Even the batteries with power ones, you should disconnect the power to work on it. A motor gets stalled. That's something that can happen, maybe accidentally by programming, and they'll just burn up, and they'll be hot, but you won't see it, so you have to be aware of that. Various mechanical issues can happen. You can get your fingers in the gears, and don't operate on it while it's powered. The arms can move. They can fall on you if they're somehow let loose mechanically. If you use springs, you're probably loading the spring, and that's something that can come free when you don't expect it. And you're probably not going to use pneumatics, but if you happen upon a system like that, just because there's no power to it doesn't mean it's not loaded. It could be just like an airsoft gun or any kind of anything that lets off energy via pneumatics can be very dangerous. There are also chemical issues. Battery, you never want to break open a battery. They sometimes do on their own. Hydraulic fluid is corrosive and bad. You never want to come in contact with that. So, to demonstrate why you don't do things with batteries that you shouldn't. We're using lithium batteries. These guys are really, really careful about how they demonstrate this. We're pretty careful. And you can see it spark. I don't know why the line was connected while he's attaching it. I thought maybe a switch would be a better idea. But you wouldn't notice right away if you had a short, as you can see. And you know, it only takes a little freight wire or laying the battery on something wrong, or laying something on top of the battery. This is suspense. It's any lithium battery. Maybe not that big, you probably don't have, too many that are that big. And always have a fire extinguisher. That's kind of handy. So, danger. And I thought about whether to show this, but don't do this.
I do.
And this is redneck science here. See how little it takes. It really doesn't take much. So just mechanical error can cause it. So all right. That's fun. Yeah. Okay, so enough safety. What jobs are performed by robots? Everybody's probably got an answer, right? Everything. That's. Anybody have a robot that does something?
Yes, I do.
You do? What's it do? You have a computer. It's kind of a bot, and it's, it can be, and that's a good point. For the, yes, printers are, and thermostats are even kind of robots, because they're controlling motion. They're using sensors and programming to do so, and that's the requirement for the merit badge. Okay, yeah, kind of, yes. So, all right, you hear that again? They're controlling motion, they're using sensors and programming to control that. So that's the definition that you need for your robot. So yeah, they do all kinds of things. Roombas, all kinds of assembly, all the rovers, all the spacecraft, all the satellites, they're all robots. And all the nuclear plants that are being cleaned up. Okay, so there are three categories that we're going to try to consider what a robot fits into. And so there's basic remote control, which is kind of what this is going to be later. We're going to have a competition here and a great prize. And then there's telerobotic, where it's kind of remote control, but the difference is that the robot is actually making some decisions. You're giving it direction, and it's got sensors, and so it can decide, do I drive off a cliff because this guy's telling me to or not? Or there's fully autonomous, where they've been programmed and they run. Okay, so what type of robot would you use for surgery?
Surgical robot.
Yeah. Remote control would probably be a good idea, and I think that you wind up with a telerobotic doing that kind of work eventually, if it's not already, because you could probably have things that can be more careful, instruments can be more careful than you might be purely remote, but you probably don't want autonomous.
You know those watches that they do in Avatar, that's walks on and the controls don't have to be a lot.
Oh, absolutely. Yeah, oh, sure.
Could they use those for surgery?
They do, yeah. Yeah.
Well, it'd be a bit difficult.
Well, surgery's kind of difficult, but it actually gives you, it lets you hear or change the ratio of motion. So you can have larger motions in your hand, control very fine motions in surgery. It's a boom. So manufacturing, what do you think? Yeah, autonomous, you set it up, you let it go. And driving the car, could be all of those, kind of. You're kind of doing it by remote control normally. You're sitting in the car, but and I threw in the last one there just because you know, you see that camera flying over the football field. If you watch football, I'm not going to do that anymore. But yeah, that's a robot, and it's probably no, it's on guy wires, and there are motors that are pulling that cable back and forth. So you might do that fully remote, but you probably wouldn't get it right. So there's some intelligence between the controllers. They have a blink there, yeah. Okay, so there are 5 fields as they're broken down here in robotics, and so there's a human-robot interface, kinds of mobility, how you handle manipulation, how you program it, and the sensors. And these are often the kind of thing that you might be categorized into if you were doing research. You would pick one of these, but usually the beauty is you're kind of paying attention to all of these if you're building your own robot. So we'll get into this a little bit here. Isaac Asimov, you guys have heard of him. He wrote iRobot, and his laws were kind of ethics for robots. They don't really necessarily indicate how you program it, but they might, and it's something to consider. It's not really part of the badge, so I threw it in there. So that interface, it's a really wide subject. You know, what does it really mean? With the big manufacturing robots, that interface is none. You don't go near it. They put cages around them. If they're running, you're not in there because they're not sensing for you. They'll knock you right over, drop a car on you, whatever they do. Something else that they mentioned in the literature from Merit Badge are these teach pendants. You actually see them, and it's a way to interact that people use this. They have a controller, kind of like a game controller, with special buttons and joysticks, and you can then instruct a robot to perform a task if it's doing manufacturing or moving parts around or whatever it does. You can use that as the interface. And if you try to drive something that you don't quite get, I think you'd see that could be, take some time to get a handle on that. So it's ever evolving, and I think we're getting to the point where we have this natural interface where you're able to talk to robots. You can talk to your phone. You can grab the arm of the robot and make it do the thing that you need it to do, and it remembers that. Get there. So this guy is, you've probably seen this.
I've seen him.
Yeah. It's really an amazing robot. It knows how to interact. It won't walk right into people. It's paying attention to what's going on around it. There's a whole lot to it, and I don't know Japanese and I don't know sign language. However, this is the robot actually using sign language as a means for it to communicate. It could speak or it could sign, and it can listen as well. So these interfaces are advancing at just amazing rates. So that's, I'll run that later if you guys want to watch that. Okay, mobility. How do robots move? Anybody know? Legs.
Certain pressure released to different parts.
Yeah, if you're talking about actually moving the joints or parts, yeah, that's sometimes it's hydraulics or pneumatics. Any other ideas?
Air power, thrust.
Well, they're thrust, they're helicopters or planes that fly. So yeah, almost any way that something can move, a robot can wind up doing. They actually, when the 6th, was that Wednesday or Thursday? The robot completed the longest autonomous journey on the planet. It was out for a whole year. So any idea as to how that journey was accomplished? Any guesses? Well, space is a really long distance, and it's a different, on the planet.
Paddles.
Paddles, that's a good guess. That's how it happened. The Wave Glider is an autonomous robot that left San Francisco a year ago and traveled via Hawaii to Australia, completely autonomous, sending back data, taking samples. There are 3 others that are out crossing the Pacific Ocean still. Pretty amazing, and stuff's just out there. It got its power from the waves. Thing went up and down. The waves on the surface went up and down, and a paddle hanging below it was in the water that wasn't rising and falling. It's an interesting physical property that the waves go up and down at the surface, but not below. So as this thing's going up and down, this thing on the bottom is churning through the wave and paddling forward. Pretty impressive, I think. Yeah, so you're interested in that.
The Bio Robotics Lab at Carnegie Mellon University are creating snake robots. These snake robots
Just what you wanted, right?
use many aircraft degrees of freedom to bridge through tightly packed volumes, accessing locations that simple machinery otherwise cannot use. These highly articulated devices can coordinate their internal degrees of freedom to perform a variety of locomotion capabilities. These devices are versatile, achieving behaviors not limited to crawling, climbing, and swimming.
Yeah. Just saw it. No trees were harmed in making it. It's a tree they didn't want anyway. Yeah.
Spy camera. Just watching you.
Freaky good. There was another video I lost track of where it climbs up a guy's leg that way.
That would be weird. Think of how that feels.
It would have been hilarious, actually.
So any way things move in nature, they're trying to model in robotics. So how would you try to move in water if that was something? I mean, I gave a couple examples. Paddle, yeah. Propeller. Sand, you might not use the same thing, right? You'd use, what would you use? Wheels? I don't know. You ever drive your bike on the sand? Tracks, yeah. What if you have to do sand and mud? Tracks, probably. Yeah, there you go. It depends on what you're going to do. That's my point here is that there are a lot of different ways for robots to move. And tracks are cool, but you don't really need them on a floor like this. Wings are great if you're going to be in the air the whole time. Okay, so manipulation. This is a whole area, and it's essential to a lot of the goals of any robot. So you have basically 2 components. There's a manipulator and an effector. And a manipulator, instead of being the hand, which you think manipulator, root being manual, right? It's the arm. And so like the arm on the shuttle, that would be, I don't know if you remember seeing that arm in the shuttle bay, that's the Canada arm. on the rovers, and then the effector is the tool or set of tools. So those rovers actually have, you got like a Swiss Army knife on the end of those with all kinds of different instruments and drills and tools. So those are some examples of manipulation. But this amazes me when I saw this the first time. And actually, it's still.
This video introduces the demonstration of skillful manipulation using a high-speed robotic system. The hand module has 3 fingers. A developed small harmonic drive gear and a high-power mini actuator are used for each finger motion. The hand can close the joints at 180 degrees in a tenth of a second. The vision system consists of 128 by 128 photodetectors and an all-pixel parallel processing array. Using the vision chip enables various image features to be computed within 1 millisecond. This tactile sensor is a sheet-like object with only 4 wires. The sensor can measure the center position of the 2-dimensional distributed load and the total load within 1 millisecond. High-speed control improves not just the speed of existing robot manipulations. Pursuing the upper limit in terms of speed for mechanical systems, we developed appropriate new control methods for high-speed manipulation. This is dribbling. High-speed active control enables the maintaining of a periodically stable motion. We call it dynamic holding. The dribbling period is around 100 milliseconds. This is pen spin. The task is achieved due to the stability of objects experiencing high-speed rotation. The contact force and the timing of shifts about the axis of rotation are modified in real time by tactile feedback. This is drilling.
Programming.
The release method is designed so that the error of the ball direction is reduced by the apparent force, which is generated by a high-speed arm swing. In this way, we developed new robust control methods by introducing
application
features peculiar to high-speed motion. Based on such a control strategy, skillful handling of more practical objects is also achieved. This is knotting of a rope. Again, can dexterously control a flexible object with high-speed sensory feedback control, regardless of its unpredictable motion. This is grasping a rice grain with tweezers. The tiny object is manipulated using a typical human tool. High-speed visual servoing enables the modification of force between the finger and the tool.
Which is the effector.
This is dynamic regrasping of the cell phone. This regrasping consists of throwing and catching, which contrasts with traditional methods that maintain contact state. These videos show that high-speed sensor motorized fusion has great potential to produce new control strategy and new skills.
All right, that's the reaction I wanted. All right, so that's an interesting thing. Yeah, all right. Yeah, everybody keep that in mind. Okay, so programming is a major field of study. It is, goes beyond robotics. But it's basically automating things, it's a virtual world of sensors and outputs. And it's a wide field. There's a lot of different specific areas. And so if you guys are into computer gaming, anybody play video games? Right, okay. You have those other creatures running around, driving around, flying, or whatever, and they're figuring out a path. They're actually using what was once AI, it's still AI, but figuring out a path. You have to do that with a robot. You have to make a plan, where is it going to go? And that's based on input. Visual recognition, you have the ability to recognize the edges of a road or faces. Feedback loop is something that gets programmed in a lot of systems. For stability, like your thermostat is a feedback loop, and it doesn't want to fight really hard to keep something on a particular value. It tries to be smooth about it or smart about it. We can talk about that later when you guys are building a robot. Machine learning is an important part of programming for a lot of systems. The rovers are learning as they drive. They keep track of how they're advancing. They learn the soil they're on based on how far every rotation is, and that's constantly being evaluated. And then simulation is actually, you know, it's an interesting field, but it's also possibly how you guys will learn how to make robots do what you need. You don't always have the hardware, but you can work in a simulated environment, and they're generally available. Almost everything that we're talking about here, you can download the programming for it, the software for it, and you can also download the plans even for many of these things to actually build if you are that ambitious. Programming consists of various languages. There are things that allow you to do block diagrams, and there's LabVIEW, and we have EasyC is the software that came with the grant, and it lets you see program in block diagram form, or you can actually look at it in ordinary text form. And then there's scripting languages as well. So sensors, this is the last of the fields. We have all of these in this kit, except laser vision. But there is an ultrasonic sensor. That sounds cool. So, you know, they're your inputs. A bump sensor is either on or off, limits on or off, potentiometers or ranges. So that's what tells a robot what's happening. And so it can only react to what it's told. So, you guys think you're going to become professional robotic technicians or researchers? If that's the case, and you almost can't avoid it in whatever job you're going to go into. You're going to work with robots. So, probably the person who knows the most about them wins. So, if you want to be involved in making robots do things, you're probably looking at technician kind of activities and training. So, you know, these are potential areas. You could be specifically mechanical or specifically programming. And so there's the Society of Manufacturing Engineers offers a certification as a technologist, but there's a whole variety of engineering programs that would all be likely to be 2-year programs or other certifications. And if you're the one who wants to figure out how to make that hand flip that cell phone up in the air and spend all your days and nights in a dark laboratory somewhere, you probably want to go on to the highest level of academics. And anywhere in between, you could wind up involved in that kind of research. From 4-year bachelor's, having a master's or PhD. Those are all, I think everybody in this room is capable of that kind of work. And if it's interesting, I would encourage you to consider that and think about what it would take to get into that kind of a program. Everybody should be interested in math and science and pay attention to that at minimum. What's that? Okay. You got a test? Is it on robotics? All right. Well, when that test comes up, let me know how you do. So, anytime you're going to work in the field, you probably need experience to get into it. So, I recommend that you consider these options to gain that experience. If you're going to build your own stuff just as a hobby, that actually really does matter when you're looking for a job. You want to know what you're interested in. Or you could work for a company that just uses robots. Or happens to have them in the building, you don't necessarily have to work with them. But if you get close to that, that's what. And internships are a pretty common approach, but they can be hard to get. And it's slave labor. They don't pay you to come and learn. But this right here, what we're doing right now, is probably one of the best ways to get this merit badge. You will know a whole bunch about robotics. And so, right here, I don't know if you can click. That's the Des Plaines Police Department badge there. They have a robot that they actually use. This is the militia part of the police department. The SWAT team. Yeah, the SWAT team, that's what it's called. And so you can kind of see this tube that the guy on the right is holding. That's a little reconnaissance robot. They can flip that in a window or have it drive into a building if there's a situation they're not sure about. And then on the little controller there, they can watch through the camera and see what's happening. So, I got done faster than I thought I would. We have a competition. You guys want to drive this hardware that's actually yours?
Oh, yeah.
Yeah. Well, that's the Clawbot that Beck's provided. And we've got this fabulous prize for the person who can perform this task the fastest in the time everybody. There's a mini tool set that you can use for your own electronics and mechanical projects.
I have it.
If you perform the task that I assigned to you in the shortest time.
So like if it's a, I've been practicing all the
Somebody's doing it. Okay, then you have a chance to win this like everybody here. So, give me a second. I'm gonna start some videos here. You guys can watch out when I get this set up, and then I'll start grabbing guys and timing it.
So what do you get that?
The toolkit?
Yeah.
Well, yeah, you can go ahead. Get to my
My engine is
If anyone doesn't want to do this, look up Robotics. It's a great book, and will make you never want to see a robot again. Robotics. Basically, Terminator, but
You carrying luggage? I can't hear it.
No, you're not taking it, right?
What's that? Oh, sure. Whoops. Pressed the thing by accident.
Is this still recording?
Yeah. We can turn it over here.
On over by you?
Agile flight.
Those things are crazy.
Multiple vehicles can fly as a formation.
Yeah, you want to take that?
Discover the method to transition between formations in 3D.
I don't think it needs to be too secure.
The team can also navigate in environments with obstacles.
They're coming to get you. Yeah, really. Now they're showing up. This is crazy.
Is that the Shriners are gonna be doing that?
Rider bots. See them clean on top of it?
Took me a second.
turns out they were all on streets the whole time.
by 80. Okay, here's the controller. Here's the task. You must grab the tissue, bring it to the box. Drop it in the box, get back to the thing. Yeah, you can drive it for a second. It's backwards.
Or if he stands back here, then he'll be standing behind you.
No, the joysticks are flipped. So one goes forward, go forward, the other goes back, go forward. Flip you out. Wait, what? Yes, it is. But it's doable, and it's screwy.
Which is the arm control?
The front button.
How do you pull
Like
it?
air vehicles capable of operating in constrained environments without the use of an external manufacturer system are typically limited to slow and conservative flight. As a consequence, almost all of this research is done with rotorcraft and the hover regime. In the rotorcraft, the CSAT, MIT, we've developed fixed-wing vehicles capable of flying at high speeds with possibilities to move and sensors. The vehicle is equipped with an inertial measurement unit and a laser range scanner. All the computation for state estimation and on board using the Intel processor, similar to what is found in a commercially available network. We designed a custom airplane to carry the sensing and computation control while still being able to move in confined spaces. Our platform has a 2-year span and weighs approximately 2 kilograms.
Wow, pretty smooth.
At any given time, the laser can only see a 2-dimensional picture of the environment. Laser scans are depicted with yellow points representing obstacles and blue representing free space.
That's it.
Even with a pre-computed map, individual 2D scans are enough information to determine. To overcome this difficulty, we aggregate successive scans and combine laser information with the original estimation to perform state estimation.
1 minute,
Another
.718.
challenge is efficiently generating trajectories for the vehicle to follow. The complicated vehicle dynamics create substantial computational difficulties in determining
1 minute.
from point A to point B. To overcome this difficulty, we use an approximate dynamics
Who's next in age?
to map the We start by connecting a set of high-level waypoints with line power settings.
I think this is a
We then use our approximate dynamically feasible
so close to the ground.
to offset from this underwater.